Hi folks, we're going to take a look at number 10 from page 370. So we'll take a quick look at the question and draw the picture as we go along. So we got two friends here live on opposite sides of a 1 kilometer wide river. Okay, and it says Helen lives 2 kilometers downstream from Judy on the opposite side. So right now I'm going to start drawing this here. So here's my river, 1 kilometer wide. Okay, and if this is where, I guess, Judy lives, okay, Helen lives on the other side, but 2 kilometers downstream. Okay, so this here is 2 kilometers. Okay, and then it says Judy can swim at a rate of 3 kilometers per hour, and the river's current is 4 kilometers per hour. So it says Judy swims from her cottage directly across the river. Okay, so what this gives us is it gives us Judy's water velocity, so how quickly she's actually swimming in what direction. So she's swimming in that direction, okay? But of course, because there's the current, we know that this is not going to be her resultant velocity. So her resultant velocity is going to be the sum of these two vectors, okay? So here, probably should have made the size a little different here because this ends up being 3 and that ends up being 4, and so her resultant velocity looks like this. Okay, now let's take a look at what they're asking us for. So they're asking for the resultant velocity, so we're going to have to find this velocity here. And how far away from Helen's college will Judy be when she reaches the other side? Okay, so at some point she's going to reach the other side, and we've got to figure out how far she is from the cottage. Okay, so this is what we have to determine based on what the question is asking. Okay, so let's get rid of the textbook here and solve this problem. Okay, so resultant velocity, that's very straightforward. Now, in fact, that's pretty nice because you've got Judy who's swimming directly across, so perpendicular to the current. So we just have a right angle triangle. Now, hopefully you recognize this as the two non-hypotenuse legs being 3 and 4. So we should know here that that's just a 3, 4, 5 triangle. So the magnitude is just going to be 5. Okay, I'll just assume we know that. If not, you can just put it into Pythagoras. Okay, and what we need here is the angle. So the angle, I can use any one I like, but I might as well use the ones I were given. So I'll use tan. So tan inverse of opposite over adjacent. So 4 over 3. And let's get our calculator here. So we got tan inverse of 4 over 3. Okay, and we've got 53.13. Okay, so theta is 53.13. So if we want to give an answer to A, okay, we have that the resultant velocity is going to be equal to 5 meters per second. Okay, and for the direction, I think it's easiest if we just give the direction, I guess, from the shore. Okay, so phi here is just going to be 90 minus 53.13, and so that's going to be 36.87, I think, 36.87 degrees. And of course, if I was on a test, I would tell you, you better check that out. So 90 minus 53.13 and 36.87. Better to check. Okay. So here we can say 36.87 degrees from the shoreline. Okay, so there's A. So now B says, let's go back. How far away from Helen's cottage will Judy be when she reaches the other side? In fact, I just noticed there's a C also. Well, let's start with that one there. So how far is she going to be when she reaches the other side? Okay. So I know that this is going to be the route that she follows, okay? But notice here that I've got this triangle. I know that the distance across, the distance across the river is 1, and I now have this angle theta, which is 53.13. So I don't even have to use the velocity, or the whole velocity, but I do need to use that direction. So for B, okay, I can just calculate this distance here. So let's call this the distance downstream. Okay, so I guess we'll be using tangent, so we have tan of 53.13 is equal to the downstream distance over the adjacent side of that thing, which is just 1. So the downstream distance is equal to tan of 53.13, so 1.33, so about 1 1/3. Okay, so just go with 1.33. But what they're looking for is actually this distance, okay, which I'll call x, which is how far she's going to be from Helen's house. Okay, so since the total is 2, x is just going to be 1.33. Oh, sorry, it's just going to be 2 minus 1.33. Okay, so that'll just be 0.67 kilometers. Okay. So, and I just realized here, if we go back, these are not in meters per second, these are in kilometers per second. Okay, so sorry about that. We'll just change that there. Make sure everything's consistent. Okay, so that should have just been kilometers per second. Okay, so now let's look at C, which I guess I was covering up before. It says, how long will it take Judy to reach the other side? Okay, so there's a couple of ways in which we can solve this. In fact, there's 3 ways, because you can use the velocity that she's actually traveling at and calculate this distance here. And in the end, what you're going to have to use is t equals d over v. Okay, now instead of memorizing all 3 versions of this relationship between time, distance, and velocity, just remember that velocity is distance over time. And then from there, just change things around as you need to. So here, multiply t, divide by v, I get this here. Okay. What I could also do is I could work with the component of that velocity. Because these are perpendicular components, I could just work with the component of the velocity in that direction and use this distance. Okay. So you have to cover 1 kilometer across the river at a speed across the river of 3 kilometers per second. So here, distance of 1 over 3. Or I could think of it as I have to travel this distance of 1.33 kilometers, okay, at 4 kilometers per hour. Okay, so 1.33 divided by 4. Well, lo and behold, guess what that gives us? 1.33 divided by 4 gives us the exact same answer, 1/3. Okay, or I could have also calculated this distance here, okay, and then divided that by the speed, which is 5. Any one of these would work, okay, but in the end, it's equal to 1/3 of an hour, okay, or 20 minutes. If we want to put it in minutes, a little more reasonable there, okay. So just to recap this problem, number 1, it's really important to get a good diagram. Okay, make sure you're correctly using and labeling everything you've got. This ends up being a slightly easier problem because we've got this right angle triangle to work with as opposed to one that's not right angled. Okay, that's it for this one.